Whichever value would have been assigned to that shared variable in that last iteration will be the value that is carried outside of the parallel region. As an example, here we see the use of the last private on the variable x. Inside that loop, x is being used like a temporary variable and being reassigned. If you look at the last line of this example, which is outside of the parallel region, we're taking the last computed value of x and assigning it into a variable that is external to that parallel region, in this case last underscore x. So we must use the last private clause to make sure that each thread gets its own copy of the variable x to be used as a temporary work variable, but then we also want to make sure that that last assigned value of x is allowed to come out of or exit the parallel region and be used external to it. In those cases, you can actually use a separate OMP parallel Pragma. The parallel Pragma is used when you have a block of code that you want all of the threads to execute. Just like we had with the parallel for Pragma, there's also an implicit barrier at the end of the parallel Pragma, which again enforces sequential consistency because all of the threads must join at the end before we execute the next sequence of instructions. If we have a parallel region where each thread is executing all of the statements within that region using a pound Pragma OMP parallel, there may be a for loop contained in that region in which we want the iterations to be executed by individual threads. In that case, we can take and insert a pound Pragma OMP for in front of that for loop, and this will then take those iterations, divide them up amongst threads, and execute those iterations along the threads. Just like with the parallel for Pragma, there is a barrier synchronization at the end of the OMP for Pragma. This will make sure that all of the iterations are executed before proceeding on to the subsequent execution. There may be points within your large parallel region which you want to have executed by a single thread. In that case, you can surround those portions of the code with a single Pragma. This tells the compiler that you want the parallel execution to be paused while a single thread executes that block of code. Things like a print statement are going to be best executed with a single Pragma, instead of having multiple threads execute the same print statement. Just like with the parallel Pragma and the for Pragma, there is an implicit barrier at the end of the single Pragma. Another feature of OpenMP is the nowait clause. The nowait clause allows you to skip over the implicit barrier at the end of a for or a single region because you know that that barrier will not be necessary. The nowait clause cannot be put on a parallel region because that's the ultimate fork join that we want to make sure that all the threads have joined before we allow the main thread to continue in the next sequential portion of the code. Here's an example where we can show the insertion of the parallel, the for, and the single Pragmas, also with some nowait clauses attached. In this case, we have two for loops. The first for loop calculates and assigns values to the array A, calling a function alpha. Next, we check a value delta to see if it's less than 0, and if it is, print out a message. And this is followed by the second for loop, which calculates and updates values in the vector b by the function beta. The iterations for each of the for loop appear to be independent of each other. Therefore, we should be able to make them run in parallel by using a Pragma OMP4. The print statement is probably something that we want to have only one thread execute. So to execute in parallel, I add a parallel Pragma around the entire region of code. Within that, on each of the for loops, I put a Pragma OMP4. And because I want the print statement to be executed by only one thread, I put a Pragma OMP single around that. Now also, I notice that the first for loop does not have anything to do with the rest of the code. So therefore, I can skip over that implicit barrier by putting a nowait clause on that. Because I don't need to worry about the print statement completing before I begin the execution of the second for loop, I can add the nowait clause to that single Pragma and allow threads to skip around the print statement and start immediately executing the iterations of that second for loop. You must be careful when trying to apply the nowait clause. Make sure that you really do not need to stop at that barrier synchronization at the end of that particular region. Here I've changed the code slightly. So now instead of a print statement, I've got an assignment of a value to delta based upon the condition on the if test. In this case, I really only want one thread to execute that if test and that assignment of the delta variable if it needs to be reassigned. But I want to make sure that all of the threads wait at that region before executing or entering the second for loop, because the value of delta is used as a parameter to the calls to the beta function in that second for loop. Therefore, I cannot use the nowait clause on this particular single pragma. In this example, I've modified the assignment value that goes into the delta variable within the single region. In this case, I'm using values out of the A array, and so therefore I must make sure that all of the computations that are updating the A array have completed before I enter the single region. In this case, I have to remove the nowait clause from the initial Pragma OMP4 because I must guarantee that all of the updates to the A array are completed before I go into the single region that updates the delta variable. Now we have an extended example. Here I have a nested for loop. The outer loop is the for I loop that computes a value from low and high by taking out corresponding elements from the A and B vectors. It checks the values of low and high, and if low is greater than high, it prints out a message that says there's a bounds mismatch and prints out the I iteration value so that we can tell where those bounds were mismatched. After that, we go in and execute the nested for loop, which updates elements of the C array based on the J variable, which is the loop iterator. In this case, they call the function alpha with I and J as the parameters. It's tempting to put an OMP parallel for pragma around the outermost loop. Unfortunately, if we look at the code, we realize that we can't do that. The values of low and high, when they're assigned values from the A and B vectors, have no guarantee that they will be non-overlapping for any two iterations of that outer I loop. This means that values that are updating in the C array in the inner for loop may be overlapping between different iterations of the outer I loop. This means that our only opportunity for iterations in parallel are on the inner loop only. So therefore I've added an OMP parallel for pragma around the innermost loop only. But of course, this is within a loop itself, and every time I encounter that inner loop and that parallel region, I'm going to be forking and joining threads, which is going to give me a performance issue that I want to try and eliminate if possible. One way to eliminate all of those forks and joins is to actually make a parallel region that encompasses the outer for loop itself. Each thread will execute all of the iterations of the I loop. They will make assignments to the low and the high variables. They will make the test to see whether low is greater than high and print out a message on the bounds mismatch. At the point that they reach the innermost loop, we have an OMP for pragma there, which will make sure that those iterations are divided amongst the threads. Of course, we want to make sure that each thread has its own copy of the I and the J and the low and the high variables. And so on the outer pragma, we've added a private clause for I, J, low, and high. Of course, since we have a print statement in there, each thread is going to be executing that print statement. But we probably only want one thread to actually do the print statement itself. And of course, to do that, we just need to add a single pragma on that print statement. So here we see that the Pragma OMP single with a nowait has been added to the print statement. The nowait will guarantee that those threads that are not chosen to execute the print statement will be able to go on and start execution of the inner loop iterations. To summarize, we've seen how to identify for loops that can be executed in parallel, how to identify blocks of code suitable for parallel execution. We've seen the OpenMP pragmas that can be used to make parts of our code run in parallel and to divide up those for iterations into loops. We've discussed some of the OpenMP pragmas that are available to parallelize code and divide up loop iterations amongst threads. And we've also seen how best to use the single and the nowait clauses. For more detailed information on OpenMP, or to find out more of the pragmas that we didn't have time to cover in this module, if you want more information or details on the OpenMP pragmas that we've covered, or those that we have not had time to cover in this module, please consult any of the references shown here. This brings us to the end of Part 3. There are 2 labs that are attached to this module. Each of them will give you source code that you can take and make parallel with OpenMP pragmas. Please look for Part 4 in the Introduction to Parallel Programming sequence. Thank you for your interest.